So we're going to learn how computers work in this video, and some of the things we're going to cover are circuits and switches, coding schemes, binary, 2 to the power of n, so that's 2 to the power of n, not 2n, even though that's not up at the top, 5 generations of computers, Moore's law, bits, bytes, kilobytes, megabytes, gigabytes, and terabytes. How do we measure bits? So I should maybe put that in there, measuring bits. And what bits are, right? We'll learn what that is, and we'll learn about machine language. And then I'm also going to give you a resource for learning a lot more about computers. So you could come to YouTube Todd McLeod, and if you go there, I'll give you this resource just right off the bat. And then come to playlists, and then you could go to even more. And then the playlists that you're looking for all begin with like week 01. So let's see. Here we go, like week 16 ethics, week 08 networks and networking, week 02 computer concepts. Like this one right here. So what I'm going to teach you is like pretty much what I teach in my introductory computer concepts course. And so you're going to get this stuff right here. But maybe you want to see a little bit more about how hardware works and the role memory plays and the different areas of computer remembering, like cache, registers, RAM, primary storage, secondary storage, volatile, not volatile, what all that stuff is. So if you want to check that out, you can come in and watch these like week 3 and week 4 right here. I'm not sure what week 5 covers, but week 2, right, that's what we're going to be talking about right now. But if you want more, you can watch week 3 and week 4. So that's a good resource for you. All right, so let's take a look at this, how computers work. This is the first thing you need to know. Computers run on electricity. And like that's just like the foundation. And at the end of this presentation, we're going to get back to this idea of the power switch. And you know, the power symbol in computers is this power symbol. All right, and that's the power symbol, universal power symbol for on or off. And what this is actually composed of is a 0 and a 1, because something can be off, 0, or it can be on. And this is the foundation of how computers work, right? Like computers run on electricity, and electricity can be either on or off. I know there's like dimmer switches too, and there's like states in between on or off. It's like dim, but let's just look at the discrete ends of that spectrum. Electricity can either be on or off. And based upon whether or not electricity is on or off, we can encode a message and we convey that message. Now that sounds confusing, but just think about, or it could be a little bit confusing, but just think about your porch light on Halloween. Whoa. Hopefully a light bulb just went on over your head. Your porch light can be on or off, right? And if it's on, what does it mean? It means come trick or treat on Halloween, right? And if it's off, it means, you know, we're out of candy. Hope you had a good time. Go to some other house, right? So with a light, with a single light, we have been able to encode and convey 2 messages. If that light is on, come trick or treat. If that light is off, go away, we're all out of candy. And that, my friends, is like, that's it. That's how computers work. That's it right there. So they run on electricity. Electricity can be on or off. And we can encode and store and convey. So we can encode, store, convey, you know, meaning based upon whether or not, you know, the light switch or the circuit is on or off. So when I use the word circuit, when I use the word transistor, when I use the word switch, all that means is that something is on or off, right? It's just some way of sort of turning something on or off or measuring if something is on or off. Yes, there are nuances between a transistor and you know, maybe a transistor and you know, a switch or a circuit, right? And definitely between transistors and silicon wafers and chips and vacuum tubes. But at its heart, it's like a light switch. That's all it is, right? Something can be on or off. Circuit, transistor, switch, on or off. So computers run on electricity. Electricity has 2 states, on or off. And if we have one light bulb like our porch, we can convey 2 messages, right? So, you know, come on in, come trick or treat, or go away, right? So it could be that. And so we have coding schemes. So the first thing you need to know about computers, they run on electricity. Second thing is that we could create coding schemes based upon whether or not a circuit or a switch is on or off. right? So one coding scheme is like the porch light on Halloween. If we have 2 lights, and pause the video here, but if we have 2 lights, how many messages can be stored and conveyed, right? So just imagine you're sending some message to your friend across the street. You have 2 light bulbs, right? How many messages can you send to your friend based upon the configurations of on or off of those 2 light bulbs? How many messages can you send to your friend? So pause the video, think about that for a second, and see if you can answer it. And then here's the answer. 4. Right? Because they could both be on, they could both be off. One could be on, the other could be off, or vice versa. And so you could create your own coding scheme, and you could say, hey, the arrangements of these lights, if they're in this arrangement, they mean these things. And if you tell somebody that coding scheme, they can look at those lights, and depending upon their on-off configuration, they know what you're trying to convey. So if we have 3 lights, how many messages can we convey? Right? So pause the video, think about it, see if you can come up with the answer. And now here's the answer. We could convey 3 lights, we could convey 8. And the way we do that is the formula is 2 to the power of n, where n is the number of lights or the number of switches we have, right? So 2 to the power of 3 is 2 times 2 times 2, which is 2 times 2 is 4, times 2 is 8, right? 2 to the power of 4 would be 2, 4, 8. 2 times 2 is 4. 2 times 2 times 2 is 8. So 2, 4, 8, 16. With 4 lights, we could convey 16. With 5 lights, we could convey 32. With 6 lights, we could convey 64. With 7 lights, we could convey 128. And with 8 lights, we could convey 256. And you hear those numbers a lot around computers. And the reason you hear those numbers is because computers are base 2. They're binary, right? And the reason they're binary, and we have binary digits, bits, right? Binary digits, bicycle, 2 wheels, biplane, 2 wings, binary, 2 digits, right? Binary digits, on or off, 0 or 1. And because it's binary, right, we've got 2 digits, and everything is multiples of 2. It's 2 to the power of n. Well, how many lights do you have? Right? I have 3 lights, I can convey 8 messages. I got 2 lights on my porch, I can convey 4 messages. I have 1 light on my porch, I can convey 2 messages. 2 to the power of n, where n is the number of lights, right? So if we had 3 lights, we could convey 2 to the power of 3, or 2 times 2 times 2, or 2 times 2 is 4, times 2 is 8. So there are the 8, and we could create our own coding scheme. There it is. Right? And instead of saying on or off, we could say, hey, 0's for off and 1 for on. And that's why with computers, we see all these 0's and 1's. All it means is there's some circuit or there's some switch that is on or off. Now, this is the mind-blowing thing about computers. It's a really basic concept that something can be in an on-off state, and it can mean one thing if it's on and another thing if it's off. That's a really basic concept. But computers take that concept and they scale it to the level of billions, right? So being able to check billions of circuits and seeing if those light switches, so to speak, are in an on-off state, and being able to do that quickly, billions of times a second. Holy cow, that's the power of computers. And that's everything in a computer is just a 0 or a 1, which means it's a circuit in some configuration of on or off. And that configuration of on or off means something. Somebody created some coding scheme. So it might mean that, this arrangement of on and off, 0's and 1's, means it's this color red. Or a slightly different arrangements of 0's and 1's, circuits in an on-off state, it's a slightly shade different of red, right? Slightly different shade of red. So it's really a truly amazing concept that this is how computers work. But that's all that's going on beneath them. And that's how we get to 0's and 1's. So if that's new to you, that's awesome. Because I love sharing that with people and watching them go, whoa, really? That's amazing. It is amazing. It's totally amazing. So we could do a coding scheme like this, right? Where I have the on-off represent letters. And then I could, create, I could have circuits in a certain arrangement of on or off, and I could create a message. So pause the video again right now. And right here, I want you to figure out, what does this message say? So 001 would be B. So I'd put a B here, right? So that's B. So pause the video and figure out what message did I store here with storing certain on-off states. All right, so here's the answer. It's all I could come up with with just the first 8 letters of the alphabet. That's all I could come up with. So there we go. That's kind of interesting.